Our next talk is freeing identity from infrastructure, automating virtual cloud IAM in a multi-account, multi-cloud environment. Lot of great IAM talks this morning. Many notes to take away from this. Before we get started, I want to quickly thank our sponsors, especially Tenable, for security leaders that must reduce the risk of breaches while balancing limited staff and budgets. Tenable Cloud Security is a comprehensive cloud-native application platform that simplifies the identification and remediation of cyber threats across multi-cloud and hybrid environments. Unlike siloed tools that offer fragmented visibility and limited context, Tenable discovers and maps every cloud asset identity and risk, identifying toxic combinations and attack paths that pose the greatest threat to your business. Detailed remediation instructions, developer code, and automations improve productivity while reducing cost and risk. As always, questions immediately afterwards. Raise your hand and I'll come find you. Please welcome Ian Ferguson.
Good morning and welcome to Freeing Identity from Infrastructure. I'm Ian. I'm an engineer at Datadog, where I work in our infrastructure group that builds and operates our cloud and Kubernetes platforms that we run our products on. One of the things I work on a lot is identity and access enablement and the layer that we use for our applications to be able to interact with external services, including cloud providers. Organization runs dozens of Kubernetes clusters, tens of thousands of hosts, and millions of containers in a multi-cloud environment that includes AWS, Azure, and Google Cloud resources. When we designed this infrastructure, we had to ensure that the hundreds of engineers working on our product could safely and easily access resources across these different cloud providers from their applications. Over time, in doing this, we found that baking identity and security-focused automation into our runtime platforms allowed us to produce a system that was good for engineer experience, operator efficiency, and security efficacy. So before talking about what we do now, we're going to talk a little bit about what we did back when we were migrating from running on a single cloud provider using virtual machines managed by Chef to running in this multi-cloud provider, very Kubernetes-based world that we run in now. As we did that, we gradually evolved our human and technical infrastructure for managing cloud provider access by moving from manually provisioned and configured IAM identities, that I'll talk about a bit in a second, to automated IAM configuration and delivery across pods hosted in all of those providers. So initially, to get our pods access to cloud providers, we primarily use two things. Cubed IAM for AWS access, and static service account keys loaded from KV storage in HashiCorp Vault for GCP access. Unfortunately, these had some limitations for us. Cubed IAM only works on AWS virtual machines, and this didn't really work for us in cases where we were running pods on Azure or GCP and needed access to AWS accounts. Additionally, it runs as a daemon set, which is a process that runs within a Kubernetes node, and you can think of it as being sort of shared by all the application pods running on that node. So that meant that Cubed IAM ended up with a lot of access to assume role into different roles for all possible applications that might run on one node. And this became an increasing security risk and challenge for us as we started to bin pack more different pods onto nodes to get more runtime cost savings. And lastly, with Cubed IAM, the role selection is based on annotations that are put on namespaces and pods. This is really great for users to get going quickly. It turned out to be less great for us long term because it meant that anyone who could emit pods and get them to run on node groups that had Cubed IAM running on it could select not quite arbitrary roles, but they had a lot of flexibility to specify what roles they wanted to, just by being able to admit a pod to any of the clusters. On the GCP side, we're using static service account keys. I probably don't need to tell this audience why it wasn't great, but a few highlights, or lowlights really. It required a human admin to create and coordinate with an engineer who needed access for the application to create a key, to create the identity for it, to store it somewhere they could get it. This made managing ongoing rotation and management of those credentials very, very difficult. So both of these approaches really led to a lot of things that were bad for, again, usability, security, and reliability. They tended to lead to multiple services sharing one cloud provider role, which made it very difficult for us to audit access policies and to start to right-size those access policies in a way that was safe. One of the first things we saw was we said, this policy has too much access. We all think it's going to be safe to remove this access this application doesn't need. We remove a policy stanza and then cause an incident in production with another service that we were surprised to find out was using that. Another key downside to both of these approaches for us was that they required a lot of rote manual work and configuration by our engineers. This could be a magic annotation on a pod, like I mentioned. It could be having to figure out how to write a set of credentials to Vault and then how to make a PR to update a Vault access policy to let their application read that, or maintaining code to then read the credentials from Vault and figure out how to attach those to their AWS clients or the GCP or Azure clients in their code. All of the things I just said are ultimately low-level details that didn't really differ per application, and that we wanted to take care of as a platform for our engineers. They didn't have to keep doing that over and over. So some of the ways we started automating access, I mentioned we use HashiCorp Vault across our systems pretty heavily. We use this for static credential storage, but we also use it for ephemeral cloud provider credentials, TLS certificates, OIDC, JWTs, and more. We found repeatedly over time that asking our engineers to write and manage Vault access policies themselves was a huge source of friction and frustration for our users, and misconfiguration and challenges for us on the security side. So one of the first ways we started to remove this rote manual security work and configuration work from our users was to start using Vault policies templated on services identities, which in our case is based on the Kubernetes namespace and service account. What I'm showing here is a snippet of Vault access control list from a policy that we use to safely grant all services access to resources that are tied to that service's identity by default without users having to set this up. These particular stanzas allow every workload to automatically access temporary Azure credentials for their application, as well as some stanzas that are related to issuing TLS certificates based on their application name as well. Again, absolutely no setup for them. We take care of doing all of this. And if you're running a thing in a single namespace and service account, you can access your things, but nothing else by default. Roughly each of these template ACLs or sort of pairs you're seeing right now corresponds to a Vault secrets backend role. So to explain that a little bit, Vault has a concept of secret and auth backends. Auth backends just define a way to take a credential from some other system that's able to express identity and transmit the trust in that to Vault, and saying you can exchange this AWS proof of identity or this Kubernetes proof of identity for a Vault token that then lets you talk to Vault. Vault secret backends just let you trade that Vault token that expresses your identity and policies within Vault for credentials to access other systems. This could be static KV things that I mentioned. It could be ephemeral AWS credentials. Within the secrets backends, I mentioned the word role. A secrets backend role is just a pre-configured bundle that says, here's a configuration, and when you use this secrets backend role, let's say it's an AWS secrets backend for an AWS account, we make the role, and it basically says, use these role ARN parameters, use this TTL when you create it. It's just a pre-configured bundle of configuration for getting that credential to another system. Excuse me while I move a automated update notice I just got, which I'll be installing right after this. So most of our secrets backends have. So yeah, each of these roles are configured to issue, let's say in the case of AWS, a set of STS credentials for a single IAM role. And we set one of these up for each of our Kubernetes service accounts. When we see the service account running somewhere, we set up a role for it automatically. And then when our Kubernetes service account is running, it then calls that pre-configured role in Vault that it has access to for just itself, and it's able to get STS credentials. Just to give a little more of a concrete example on this, if we had an application running in the Frostbite Falls namespace using the service account called Bullwinkle, one of our controllers would see that get admitted to the cluster. It would configure a Vault AWS role at the path cloud-im/AWS/ an account number /STS/Frostbite Falls Bullwinkle. You'll see that last little bit matches up to sort of how we're doing that templating of namespace underscore service account in the last slide. That role would be configured to point at the dd.frostbitefallsbullwinkle IAM role in that 601 AWS account if it exists. And the service account would be automatically entitled to call that secrets backend role and no other ones using those identity templated policies from the last slide. The IAM role itself and the policies for it are still created out of band, but it's done in a way where largely engineers see it as, I'm attaching this IAM policy to my Kubernetes service account, and then we automatically generate the IAM role for them. So this was really good for usability, security, and reliability. Moving the point where you're brokering from the Kubernetes service account to a cloud provider credential off of every individual node in the fleet and into hardened and controlled Vault API services, let us minimize which IAM roles a given Kubernetes node could access at any particular time to just the ones that were tied to what that Kubernetes node was running based on the Kubernetes API at that time. The consistent one-to-one mapping of Kubernetes service accounts to cloud provider roles has really helped us in incident response and security management as well. People can tell with a really high confidence at a glance which service uses a specific IAM role, and each IAM role is used by one and only one service. So it makes it really easy for us to reason about what is probably using this, what is the blast radius of this if we modify it for reliability things, or what is the blast radius of this if there's a security incident related to it. And lastly, but very important, auto-configuring these roles and using these default templated policies drastically cut down on the amount of configuration our engineers needed to do just to get their service IAM credentials or GCP service account credentials. But it sort of lacks at the last mile. It didn't help those applications consume that access at runtime. They were able to get credentials, they could call Vault. And so to address that, we have a system we call Emissary. Emissary is a zero configuration injected sidecar container that provides access enablement services and emulates cloud provider instance metadata service APIs. So just to unpack that a bit, it's a sidecar. This is a container that runs within the pod that the application is running in. And the application can expect that to be present at all times their application is running. It's injected. We don't have our users configure this as a container in their Helm charts or their other ways of managing Kubernetes deployments. We look for a specific annotation. It's a single line. And when we see that, we have an admission controller that automatically injects the fully formed with the correct current configuration, correct versions, things like that, container into their chart. So the users don't have to worry about how do I configure Emissary. They just say this pod requires these sorts of credentials. Please give me an Emissary, and we give it to them. It's non-configurable. Turns out that when engineers have problems accessing cloud provider credentials and maybe they get a 403 accessing a bucket they really think they're supposed to be able to access, they come ask us for help because they were trying to do something else. They were trying to make a new feature. They were trying to deploy something. And they tend to not look immediately at their pod spec and start debugging these low-level things that aren't really things they think about day to day. And so by having zero configuration, we're able to give our engineers a lot more consistent experience so they can sort of intuit, like, this is how access works. And they can use their intuition from one application or one deployment, and it's going to match their expectations on others. There's no hidden gotchas of, like, you're using Emissary, but in this particular part of the infrastructure, it works different. Emissary works very, very commonly and very, very uniformly across our infrastructure. So this gives us a lot fewer cache misses, whether that's on application engineers trying to intuit how they can interact with it, or whether it's on the support side when we're trying to help understand why something isn't working. To do all this, Emissary is using the pod's Kubernetes service account token that Kubernetes issues to log into Vault and retrieve those cloud provider credentials using some of the things we just discussed. One other thing worth mentioning here is that because Emissary is just another container in the pod and not outside of it, it doesn't have any special access on its own. It's using that service account token that I mentioned, but we already default assume that everything in the pod can get that. And so it doesn't have any special access out of the box, and we're able to, it makes it easier for us to reason about the security boundaries because we're not adding a new layer of authorization or brokering of credentials. So I mentioned calling Vault, and to start to unpack how Emissary works, we're going to start with, we're getting credentials from Vault, so how is Emissary doing that? Calling Vault requires logging in, one of those auth backends I talked about earlier, and managing the renewal of the Vault token in the background. Vault tokens don't last forever. Some are renewable, some have a fixed time window, and we have to do another login. And ultimately, we found that having this code running in user applications was fairly buggy, it was fairly complex for them, and so we moved this into Emissary. And to address this, the way we moved it in is we put a full Vault authentication proxy inside of the container. And how this works is Emissary logs in using that service account token. It has its own Vault token manager. It logs in, it renews it, and then it sets on the pod specific environment variables that Vault clients and SDKs are set to use. You'll see one later that's Vault_adder to configure themselves. And those clients will auto-detect that value and say, when I'm sending requests to Vault, just send it to this IP address that Emissary is listening on. And then the application will send a Vault request. It will go to the Emissary container. Emissary will see that request, take the Vault token it has in cache and it's maintaining for that application, add it to the outbound request, and then proxy that to the underlying Vault cluster. If you're familiar with the Vault agent functionality that was introduced in the last few years, this is in fact very, very similar to it, and at this point uses some of those components. So this was good for usability, security, and reliability. People weren't having to figure out Vault login code, weren't accidentally logging those tokens, or having losing access to things because their asynchronous code to renew things in the background was failing. And it gives a really easy way where things can access Vault by just doing a single vault.read call using a standard Vault SDK without any extra login and anything. And we're also able to bake in client-side caching that I mentioned a little bit and rate limiting into Emissary, which gives us really consistent resiliency reactions when we lose credential providers like Vault. So that Vault access is very neat, and the engineers could use that to retrieve cloud provider credentials from Vault by just writing vault.read, one of those cloud IAM paths I showed earlier. But wouldn't it be better if we could use that same sort of auto-configured access model where there's environment variables that tell common clients how to get credentials, but for cloud provider credentials? In fact, cloud provider virtual machines have a very similar model for enabling transparent IAM access to those virtual machines, the instance metadata service. Most of y'all are probably very familiar with this, but virtual machines running in cloud providers like AWS, Azure, and GCP have a service that listens on a link local IP address, commonly 169.254.169.254 historically, though that's starting to change in a few places. And it lets things running on a virtual machine. In this case, I'm using AWS as an example, but everything I'm about to talk about applies pretty equally for GCP and Azure from a distance. And it lets something that's running on this virtual machine that wants to talk to S3 use maybe the AWS CLI, and the AWS CLI says, if you didn't explicitly pass me keys, I'm going to go look at this magic IP address and see if it will give me credentials based on my role. It gets those, and then it sends it to S3. You get your S3 blobs. Everyone's happy. That's great. So this is a really good user experience. The security benefits are great. We aren't hard-coding long-lived credentials or even managing them directly in the code. It's all buried in SDK code that's pretty well reviewed, pretty well tested. We trust it. So the next question then is sort of, can we forklift this IMDS-based experience into Kubernetes by emulating those cloud provider metadata service endpoints? And isn't this what kubed.im that I just discussed already does? And it is. In the kubed.im example, very similar to running directly on an EC2 virtual machine, except for when you make you're running inside a pod in Kubernetes, and when you make your AWS SDK call to S3, it says, I don't have credentials, so I'm going to go check this magic IP. But rather than the thing listening being AWS mounting that socket on the link local address, it's going to be kubed.im. And kubed.im is going to look at the request, verify what pod it's coming from, map some roles to it, get the role for you. But then at the end of the day, as a consumer, it's returning STS credentials to you just like AWS would. The default SDKs all work with that. They call S3, you get your blobs from blob storage, and everyone's happy. So this works pretty well, but it has the limitations that it only works on AWS nodes because kubed.im is ultimately just proxying the requests to the EC2 host's IMDS server. And also, we now have this blob out here that is running outside of the pods, and we have multiple pods from different applications calling it. So the security properties of how does kubed.im make sure that it can't be tricked into giving a different pod different credentials start to matter. It's not rocket science. It's not impossible. But I'm not a very bright person. And I don't like to have to think about more than I have to. So it's not great. So what if we combined this emulated IMDS API idea with those Vault secret backends that do ephemeral credentials and that automated identity-based access enablement to provide sort of transparent, zero configuration cloud provider access to our pods? And it turns out that's exactly what you can do. And this is how we do IAM at Datadog today, is we emulate all three cloud providers, IAM metadata services, and Emissary. Similar story as last time, except for this time, instead of getting to kubed.im, you get to Emissary that's running in your pod, has your pod's identity. And instead of calling the IMDS socket on the host, Emissary knows how to talk to Vault. And then Vault applies those authorization policies and uses its access to ultimately call AWS STS or impersonated service accounts in GCP, and then return the credentials. They all get returned up. And from the point of view of a person running AWS S3 cat or copy, it works exactly the same as running on a VM. So this all works identically from the client perspective as if the client were running on that VM. Importantly, not just if the pod's running on AWS and talking to AWS, but it also works if we're running a pod on Azure and want to talk to AWS, or if we're running a pod on AWS and want to talk to GCP. One of the other big bonuses for us here is that using those cloud provider IMDS APIs as the interface means we get all of the credential handling and interfaces from cloud provider SDKs for free in different languages. At Datadog, we have engineers working in numerous different programming languages. And so having something where we don't have to write all of those layers of Vault login and AWS and GCP and Azure ephemeral credential management and renewal in 5 or more different languages is a huge benefit for us. So taken all together, this approach allowed us to safely and transparently provide Kubernetes pods access to resources and cloud providers and accounts independently of what cloud provider the underlying virtual machine was in. And without, and probably most importantly for us in many ways, engineers ever needing to write any code in their services to retrieve or use those credentials. So earlier this morning, we open sourced a small subset of this, specifically the IMDS features that we use in Emissary as a project called Attache. I'm going to very, very quickly switch over to my terminal now and demo using that in concert with a local Vault server I'm running to fetch some files from AWS S3 using the AWS CLI and some files from, so I'm using my mouse where I can't see it, from GCP. This will be fun because I'm not mirroring my display, so I will also be looking at this one. Let's see where I am. Woo. OK, so in the top left, I'm running a Vault server. The color-coded JSON is Vault audit logs from that Vault server. The bottom left is where I'm going to start up one of these Attache containers. Attache is, again, just sort of a subset of Emissary. It's going to mount some IMDS listeners. And the right is where I'm going to run things as soon as I click on the terminal. Cool. All right, so if we were to run this AWS S3 cat command right now, it's going to fail because I'm not running any listener. I don't have any credentials. All right, and then, so I just started an Attache server, pretty normal looking Golang server startup stuff there. That's fun. This is still not going to work. Oh, I already had it working in that environment. So it did work this time. I'll talk about why I didn't think it was going to work real quick and then wrap up the demo. The reason I didn't think it was going to work is this particular server, I mentioned that historically the link local addresses of 169.254, 169.254 were used. As different cloud providers rolled out things like Elastic Container Service or Managed Kubernetes, that had some similar limitations to sort of if you look at a distance from maybe kube.im where you don't want everything sharing one socket and one address on one VM. They started to support dynamic IP assignment of those things. And the way the SDKs pick those up is, again, magic invar variables. I thought in the right that for my prep for this, I had not set that yet. So I expected it to fail because I'm running this Attache not on that link local socket, but on a localhost socket with a random port. So sort of gave away the punchline earlier. But because we have Attache running and listening, because this one environment variable is set on the right, we were able to run this AWS command. Even though it's on my laptop, there is no IMDS. I have no other credentials present. And then we were able to see Attache receive the request. And then just above it, we were able to see audit records of Attache calling out to Vault to get the credentials. This works for GCP as well. And let's see if can someone in the front row tell me if that says bash or cat? Cat. Cool. Let's see if we can do this together real quick. OK, that's at the lead, CATBASH, and then it says client.shell probably. Yeah. Cool. OK, so this is the script that was at the very top right when you saw it. It's just going to run without those environment variables set, so it won't target the right thing. It will run with them, and then voila. So that's AWS, and that's GCP. And we were able to get everything we wanted. So thank you all for your time. And I will swap this back, and we can do questions.
Love to see an open source release before lunch. Awesome. Give us something to play with. Questions? This is the problem with the lunch slot. I'll start with one. It seems like everything is tied to the namespace and name of the service. What do you have to do to sort of govern and issue those?
Yeah, that's an exceedingly good question. So we run across numerous clusters within each of our failure domains or isolation things. We trust some of those clusters a little more than others at times, but we also, it's very important to us for engineers to be able to move workloads across different clusters, whether it's for reliability reasons, capacity reasons. If they had to update all of their IAM access and network references every time they move clusters, it doesn't work well for us. But because of that, that means as an infrastructure group, we have to take a much more keen interest in what namespaces things are running. The way we do this is maybe similar to how people run hundreds or thousands of AWS accounts, and you sort of give a team an AWS account and say, within some reason, I don't really care what you do in here. We do a similar thing with Kubernetes namespaces. So we register them centrally. It's similar maybe to a domain name model where if it's unclaimed, you can register it. This keeps our users moving fast if they're making a new service. and it's got a new name, it doesn't collide with anything, they can get going, they don't need central review. And then we have to apply a little bit of frameworking, I'll say that now, to be a little bit careful about which namespaces can run in which places based on maybe product or security sensitivities.
Any other questions? All right, let me give you guys lunch details.
Yeah, got one there.
Oh, wait. Oh, sorry. Cool. Excellent. One more.
Yeah.
Great presentation. Thinking about running Attache in like a hybrid environment, say from like OpenShift. Obviously, you're using Vault today, but thinking about like how would you, if you have like an on-prem environment, authenticating to other on-prem, services too in a hybrid network. What changes would you need to make?
Oh, what was the last bit?
What's that?
What was just the very last thing you said?
What changes would you need to make to Attache, or how would you, what advice?
So right now it is, this is taken fairly closely or almost exactly in many places from what we run in production. And because it evolved very organically in some places, like the Vault providers aren't necessarily behind an interface you can swap out today. If there's wider interest, it's something we could look at doing. In practice, internally, we, for several of the providers, are increasingly running not wholly or not on Vault for the credential management. We are using other internal APIs that are specific to us. So in that sense, theoretically, it's very possible. The magic here is sort of all the pieces together, and that you just have pre-canned written the code that knows how to call whatever server happens to give you the credentials. So I guess to sum that up, internally we do that currently. Attache is pretty hard-coded into Vault, but not in a way that we couldn't necessarily swap that out and start to give it an interface where you can say this is how you get AWS credentials in my on-prem environment using whichever things.
All right. I think we got to let folks get to lunch. First, I want to say thank you, Ian.
Of course.